So in our chapter on coordinate proofs, we have transitioned out of the proofs, but we're still looking at problems that involve coordinate points. And so we're going to talk about perimeter and area of rectangles and triangles. These are things you've seen before, but they come to us on the coordinate plane, and you'll see that in example 1 down below. Just to get us started, remember that when you're talking about a distance around an object, meaning you're going to walk around the outside, that's called the perimeter. So when they say find the perimeter, they mean distance. It could be the distance formula in some cases, or it could just be you're adding up the total lengths of each side. And then, of course, if you're talking about a region, so this is not a length, this is a space. If you're talking about the region enclosed or inside of the object, we call that the area. We're doing both today. We'll be doing both areas and perimeters on the same problem. You might remember that with your rectangle we have a side called a base and a side called a height, but remember the base is not always on the bottom because we can rotate the object anyway. So I often use the length and width, or you could use any two letters you want, X and Y. You might remember that your area formula of a rectangle is one side times another side. Here we're using the B and the H, so base times height, or length times width. And you might remember the area formula for your triangle is 1/2 base times height, or sometimes you'll see it represented as base times height divided by 2. I'll just set it up this way. Now remember, when you're comparing your height and your base, the height is always perpendicular to the base, and so perpendicular lines form right angles. You can see that here in your rectangle. And in your triangle, there's the height, and it is perpendicular to the base. Now what we're doing is we're taking a look at polygons that aren't just triangles and rectangles. What if you have something with a lot of sides? Like here we have a pentagon. In example 1, you can see we have vertices for points A, B, C, D, and E. So this is what we're talking about when we say we still have coordinate points. We're still looking at the kinds of math problems that we can do with coordinate points in this chapter. And we want to find the area, and we want to find the perimeter. So we'll get to each of those things in turn, but I went ahead and I plotted those points so you can see what it looks like. Obviously, we don't have a formula for a pentagon, right? So the technique that we're going to use here is we're going to divide that polygon into smaller figures, meaning if we can carve out the space into smaller rectangles and smaller triangles. We'll do that by using, it's not just any old line. It has to be horizontal and vertical lines. If you try to draw a slanted line, like a diagonal for instance, that will only lead to trouble. Here's an example. If I were to look at side AB, side BC, and connect point C and point A, thinking, hey, there's a triangle, I can find the area of that triangle. Well, it's going to be difficult in many of our cases because you have to find the base, you have to find the height, and it's not impossible here, but it is more challenging. And if you try to divide the shape up like this, again, it's not impossible, but there are just easier ways to do it, and we do that with horizontal lines and vertical lines. So if you have a slanted line like this, you can create a triangle out of that. We'll see more examples of that on the next page, but here's a slanted line. So let's create a triangle. You can see that point B is directly to the left of point D. Point B and D are on the same grid line, so we could connect the bottom side of this slanted line at point B with the bottom side of the right slanted line at point D. And if you do this, now you can see that we have a triangle with a base that is on the horizontal. And so that was a challenge we had earlier. If we were trying to divide it up some other way, it's hard to find a base and a height that are perpendicular to each other. Again, not impossible, but this is just more efficient. So there's your triangle, and on below that you have your rectangle, right? And so that's what we're going to do. When you divide it up into these different regions, you want to, especially if you have a lot of regions, you want to number them off. We can call this region number 1, region number 2, so that when we find our areas, we'll find the areas of each region and then add them together. So this is the area of region 1. All right, so area of region 1, which is the triangle. So we know that's going to be 1/2 times the base times the height. And so the base is a horizontal line, so we can just count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1/2 times the base of 10 times the height of. And the height has to be perpendicular to the base. And let's go to the top vertex there on your triangle. So this is your height of 1, 2, 3. And so that will give us 15. Now, we don't really have units provided to us, so we'll just call them square units. Letter U for units, whatever the units happen to be, and these are square units because of the area. Now, region 2 is a rectangle, so that area is base times height. So the base is, again, 10, and the height is 1, 2, 3, 4, 5. That'll be 50 square units. And now we're going to total them up. So T for total, we're just going to add up those two, 15 and 50. We get an answer of 65 square units. So that's the strategy, and we're going to see another problem that's much more complicated and involved on the next page, but that's the basic idea. If you have an elaborate polygon, divide it up into smaller regions. This is a common problem-solving strategy in general. If you have a problem that's too big, you divide it into smaller projects or smaller tasks or smaller things to accomplish. And you chip away at the larger project, one piece at a time. Now we still have to find the perimeter, so we're going to do that next. Let's start off with segment AB. Again, that's a vertical line. We can just count that distance, and we know that is a length of 5. In fact, on the opposite side, you can see segment DE should also be the 5. And on the bottom side here, segment AE, that'll be the base, that's 10, right? So we can count those directly, but if it's a slanted line, as you know, counting is not possible. We're going to use our distance formula instead to find the distance from point B to point C. And that's where we're using our coordinate points for the distance formula. All right, so from B to C, x coordinates -3 and 1, -3 minus 1 quantity squared plus. And the y coordinates are 3 and 6, 3 minus 6 quantity squared. That'll give us a -4 that we need to square and a -3 that we need to square, which will give us 16 and 9, which gives us root 25. That's a perfect square, so that happens to be a length of 5 of all things. Now for the length CD. We have a 1 and a 7. I'll set it up this way, 7 minus 1 quantity squared plus. And then we have a 3 and a 6 that we need to subtract and square as well. So that gives us 6 squared plus -3 squared, which is a 36 plus 9 under the radical. That gives us a root 45. Now, because we are trying to find the total distance around the object, we're going to be adding up these lengths. And it doesn't work to simplify the radical because we want to combine it with the other lengths, which are integers. So here we will use a calculator and get a decimal approximation. We'll go to 2 decimal points. And then we are going to, so we get 6.71. And then we're going to add up all 5 sides. So the total perimeter, remember it's a distance around the object. So if we start at point A, we go up 5 units, over 5 units, down to 6.71 units, down another 5, down another 10. We've gone all the way around once. That's our perimeter. I think I have them all. 1, 2, 3, 4, 5. Yeah, so we add them all together. And we're going to get about 31.71. And again, we don't have a units provided, so we just use the letter U for units. These are not square units. Square units is only for area. These are just linear units, so 31.71. So that's what we're talking about here. If a polygon is in the coordinate plane, you can use the distance formula to compute the perimeter, and that's what we were just doing right there. So let's take a look at another example. This is a big one. Here they give you a whole bunch of points A, B, C, D, E, F, and G. Again, it's a very elaborate shape, and that's the whole point. We don't have a formula for the area of this, so let's subdivide it into smaller triangles and rectangles. And those are the points up there at the top of the page. You can see them listed out all there. And I went ahead and plotted those. And that's what it looks like. Now I need to give you a couple of strategies. For example, we have this slanted line. We have this slanted line. But point D and point F are not on the same horizontal. So we have to be very careful with how we divide this up. So let's talk a moment about slanted lines, and I'll just use this empty space that we have left over. Let's pretend you have a slanted line like this. Let's pretend that's all you have. Remember, we're trying to turn these into triangles or rectangles, but we can turn this into a triangle, and the way we do that is we start at the end points. We draw lines that are either horizontal or vertical. You're not allowed to draw more slanted lines. So from this upper end point, we're going to come down, and from this lower end point, we're going to go to the right until they meet, and there is your right triangle. You have a base of 1 and a height of 3. See how we did that? Here's another example. Let's say you have a slanted line like this. I'm just making something up. We want to turn a slanted line into a triangle. So from one end point, you're going to come down. From the other endpoint, you're going to go to the side until they touch, until they meet up, and there's your right triangle. So in this case, we have a base of 1, 2, 3, 4, 5, and a height of 1. So then you can easily calculate the area by counting the base and the height. Notice the base and the height are always vertical and horizontal. So once again, a common mistake in trying to divide up the spaces in this polygon, a common mistake that I see is when students try to divide it up like this, connecting point D with point F, because that is not horizontal. And if you do that, while it might form a triangle, there's no way you can easily find the base and the height. Even if you use the distance formula and you get a value for the base, there's no way you're going to be able to find the height, because the height has to be perpendicular. And that's slanted because the base is slanted. And how do you really know where this point is? You can't calculate that height anyway. So that's just not going to work. And it's that reason why we only draw the horizontal and vertical lines, like we were pointing out earlier. So pretend that this upper left slanted line is kind of like this slanted line here. You want to draw down and across. So here we have segment DE. From point E, I'm going to come down. From D, I'm going to come across until they meet right there. That is your right triangle. Now for the slanted line E and F, again from point E, you're going to come down. And then point F, you're going to come across. You're working your way to the left until those meet. And you can see that these triangles have a very different height and a different base. Here's another slanted line from B to C. So again, from point C, come down. From B, go across until they meet. It's a very tiny right triangle right there. So that means you have this space inside. We still have to divide this up into smaller rectangles, but the space inside only has horizontal and vertical sides. So we can do this easily. We could divide this space here this way. We could divide this space here this way. There's other options. You could divide the space all the way up and down, all the way up and down. It doesn't really matter. You could divide this space here, have a rectangle right here. There's lots of different possibilities. So I'm just dividing it. We have a very large rectangle down here at the bottom. And then I'm going to take these two regions and split them left side to right side like this. So you have this rectangle here and this rectangle here. And our job is to find the area. So we're going to number off our regions. So I'll call this region 1, this triangle in the top left. I'll call this region 2. I'll call this region 3. I'll call this region 4. I'll call this tiny little triangle here region 5. And then with this big rectangle at the bottom, it's region 6. So number them off this way. That way when we do our work, we can just call them area of region 1, area of region 2, and so on. And then we'll add up all the areas. Okay, region 1, that's a triangle. So we want 1/2 base times height. The base is 1, 2, 3, and the height is 1. So 3 times 1, that'll get us 1.5. Region 2, this is also a triangle, so 1/2 base times height. So we have 1/2 times the base of 1, 2, 3, 4, 5, and the height of 2. That'll give us 5. Region 3, our base is 1, 2, 3, and the height is 1, 2, 3, 4. I guess I should write the formula first. It is a rectangle, so I'm saying our formula is base times height. So the base is 3, the height is 4. Area of region 4 is rectangle, base times height again. 1, 2, 3, 4, 5 on the base. 3 on the height, that's 15. Area of region 5, okay, so that's a very tiny triangle. That's 1/2 base times height. So 1/2 times the base of 1 times the height of 1 means you have an area of 0.5. And then our 6th and final region, another rectangle, base times height. And we're adding them all up. That should give us 70 altogether. And again, it's an area with no units provided, so we're just calling it square units.